All right. Good afternoon. Let's get started. I apologize for not being able to teach recitation in person, and also had to skip a few recitations last week. I hope you still benefit from the other TAs when they were covering for me. For today, I guess I want to open up by letting you asking questions you might have regarding the exam tomorrow. But before I do that, I just want to point out that if you have any accommodations, please contact Professor Gibson if you haven't done that. Let him know as soon as possible. During the recitation today, if you have any questions, feel free to unmute yourself or just put in the chat box. We can look at them together. Any questions you have that we should go over now? Any particular examples of just a general concept? I'm not hearing any comments. I do have several questions, several examples that I prepared. I can go over those. Hopefully you find them helpful as you study for the exam. Do I know if Euler equations are going to be on the exam? I'm not sure if Euler equations going to be on the exam because I wasn't there for the exam meeting. And from what I understood, the exam probably going to focus on the second order linear constant coefficient homogeneous equations, perhaps the higher order one. I'm not sure. I wasn't told that Euler equations is going to be on the exam, but I am going to go over one example. Hopefully that helps. And as you study for it, I think it's good to, obviously study everything since last exam, but at the same time, spend some time on Euler equations. Sorry for not giving you a definite answer there. Let me begin with this example. Again, feel free to interrupt me at any time with questions or comments. So y double prime equals negative 2y prime minus 2y. And then we're going to solve this with initial conditions. Y of 0 equals 2, y prime of 0 equals negative 2. The first thing we're going to do is we're going to move all the terms to the left, see if we end up with a homogeneous equation. So y double prime plus 2y prime plus 2y equals 0. And it turns out that it is a homogeneous equation. And the 0 tells us it's homogeneous. All the coefficients in front of y double prime, y prime, and the y tell us that it's going to be constant coefficient. It's also linear because the y double prime, y prime, and y, they only have a power of 1, and there's no products of any of them. So it's linear, and it's a second order. The order number here doesn't really matter that much, and mostly just a linear, constant coefficient, homogeneous. Which means we can use the ansatz. So suppose the solution is going to be y equals e to the lambda x. And then we can take this expression, put into the differential equation by finding y prime first, y double prime. I'm going to do them quickly since we already done that many times. Just take the derivative. Put into the differential equation, we have lambda squared e to the lambda x plus 2 lambda e to the lambda x plus 2 e to the lambda x equals 0. And then we can factor out e to the lambda x, give us lambda squared plus 2 lambda plus 2 equals 0. And based on what we learned, that in the past, that e to the lambda x is not going to equal to 0 as an exponential expression, which tells us that the remaining part, lambda squared plus 2 lambda plus 2 has to be 0. Otherwise, we're not going to have a 0 on the right-hand side. This is characteristic equation. And we can solve for lambda. If we know what lambda is, then we know what the solution will look like based on the answers. So let's solve this. We can try to factor this. It turns out that for this particular equation, we can't really factor this. Let's just use quadratic formula. So lambda equals negative b plus minus square root of b squared, that's a 4 minus 4 times a times c, all over 2a. And then that's going to equal to, when we simplify the numerator, so that's a negative 2 plus minus square root of negative 4, which is 2i. We get negative 2 plus minus 2i divided by 2, and then we can factor out a 2 from the numerator, divide by 2 in the denominator. So 2 times negative 1 plus minus I divided by 2. So the 2 cancels, give us only negative 1 plus minus I. Those are the two different lambda values, which tell us that the solution, the base solution, or the linear independent solution, is going to be, the first one is going to be y equals e to the negative 1 plus I x. Second one is going to be y equals e to the negative 1 minus I x. So that's one way to write down the base solution. We can actually rewrite this, really just distribute the x into the exponent and then rewrite it as a product of two exponential expressions. So that's going to be y equals e to the negative x times e to the ix. The second one is y equals e to the negative x times e to the negative ix. So that's just another way to put the base solution. And if you remember from lectures, I'm sure Professor Gibson went through this. When you have e to the ix and e to the negative ix, in the general solution, we can rewrite this using the base solution y equals e to the negative x cosine x, and the y equals e to the negative x sine x. It depends on the example. Sometimes it's easy to work with sine and cosine, but sometimes it's easy to work with exponential expressions. So for this, just for practice, we're going to use the base solution e to the negative x cosine x, e to the negative x sine x. For the general solution, it's going to be c1 e to the negative x cosine x plus c2 e to the negative x sine x. Any questions? If you are curious how we come up with cosine and sine, you can use Euler formula. E to the ix equals, so Euler formula, e to the ix equals cosine x plus I sine x. And then at some point, we just have to redefine the coefficients, that will give us the two-base solution here.
I don't know if you already said this or not, but is the Euler formula going to be on the test?
You don't have to use it. I guess my suggestion is that whenever we end up with complex roots to the characteristic equation, we don't have to actually apply the Euler formula, but we kind of just have to remember that the form of the base solution or the linear independent solution.
Okay, and then also, if it doesn't specify the question, which form of the answer we have to put it in, whether it's the complex form versus a sine cosine form, can we just do either, or is there one that we should go to?
Absolutely, that's a good question. I think either form that you can use is fine. If it just say, solve this, write down the general solution, I don't see any point. I don't see any problem using the exponential form versus the sine cosine form.
Okay, thank you.
Good question. So before I move on to find C1, C2, I just want to kind of remind you that if we have lambda 1 and the lambda 2 equals mu plus I omega, then the base solutions, again, there's three ways to write it, but the first two kind of the same. It's going to be e to the mu plus I omega x, sorry, plus minus, that's what lambda is. And the second one is going to be e to the mu minus I omega x. But if you expand it to rewrite this, really the same form as e to the mu x, e to the I omega x, and e to the mu x, e to the negative I omega x. So those two forms are basically the same. You're just rewriting it using exponential property. Now the equivalent one will be e to the mu x cosine x and e to the mu x, sorry, cosine omega x, and the e to the mu x sine omega x. So either this two base solution or the one above, doesn't matter which one you pick. That's just a reminder. It's also in the lecture notes, I believe. So here we found the general solution and we want to find C1 and C2. Let me double check. I believe I gave the initial condition y of 0 equals 2, y prime of 0 equals -2. If we want to use them, we have to find the derivative first. So to find the derivative of the general solution, we just take the derivative of each term. Be careful because we have a product. We need to use product rules, product rule twice. So we have C1, derivative of e to the negative x, it's negative e to the negative x cosine x plus e to the negative x negative sine x. So that's product rule on the first term, plus C2, same thing, negative e to the negative x sine x plus e to the negative x cosine x. So those are the terms when we take the derivative. Now we're going to use the initial condition. The first one is y of 0 equals 2. Take this x equals 0, y equals 2, put into the general solution. So we get, so put in here, we get 2 equals C1 e to the negative 0 cosine 0 plus C2 e to the negative 0 sine 0. And it looks like, it looks, you might be like, oh, there's a sine, there's a cosine, there's the e there. But it's really not that bad because sine 0 is 0. So this second term goes to 0. Cosine 0 is 1. E to the negative 0 is also 1. So we just have 2 equals C1. It's actually really nice. And then we're going to use the second initial condition, y prime of 0 equals negative 2. And then we're going to take this and then put it into the derivative equation. Again, that's a lot of terms, but they are two of them cancels, and you can kind of do it in your head if you prefer, or you can just write them down and then simplify. So put in there, we get negative 2 equals C1, negative e to the negative 0, cosine 0, plus e to the negative 0, times negative sine 0, plus C2. We have negative e to the negative 0 sine 0 plus e to the negative 0 cosine 0. And we simplify again, sine 0 is 0, so this term goes away. That goes away because of sine 0. Cosine 0 is 1. E to the negative 0 is 1. This is a 1. This is also 1, but we have a negative in front of it. So we have negative 2 equals C1 times negative 1 from the first bracket plus C2 times 1. That's what we have. We have negative 2 equals C1, negative C1 plus C2. And we already know what C1 is, right? C1 we had is 2. So if we put 2 for C1, then we can get C2 to be 0. Now we have C1, C2, we can put in the general solution, which is going to be y equals 2 e to the negative x cosine x plus a 0. That's it, just the first term. The second term doesn't exist. Any questions on this part to find C1, C2? It's just be careful. I know it could be confusing. Sometimes, we mistaken cosine 0 for sine 0. Always remember sine 0 is 0, cosine 0 is 1. Don't get confused there. I do want to point out that graphing wise, I know for the homework, there was a couple of problems you had to kind of provide a graph for the solution. So if we just look at the solution at the end, we look at as two parts. So here we have cosine x, and then that cosine x is being multiplied by 2e to the negative x, right? And if you remember that if you have y equals a cosine x, you probably remember back then, a here is just what we call amplitude of the cosine function, right? So cosine function looks like this. It's oscillating function, and this is what the amplitude is, right? For this particular example, the 2e to the negative x, that's what we call the amplitude function. It defines how high the cosine curve could go or how low the cosine curve could go. And it changes based on x. If we were just sketch this, what we do is that we graph 2e to the negative x first. Just a quick sketch, e to the negative x is exponential decay. So we kind of have this exponential decay. But then, because that's the amplitude function, so we're just going to reflect this function over x-axis. And then what we do next to sketch is that we just graph cosine x, but we bound it between those two dotted lines. So cosine x begin with the highest point, so begin here. It's going to come down. When it touches the lower dotted line, it's going to go up. And when it touches the high dotted line, it's going to go down. So it's really just cosine function oscillating between those two lines corresponding to the amplitude function. So that's what the graph look like. Of course, you can graph it using decimals or using any other tools that you feel comfortable with. But I just kind of want to explain that part. Questions on this? All right, any other questions before I move on to the next example? So the next example I have is we have y double prime minus y prime plus 1/4 y equals 0. And then we're going to solve this. Suppose we have some initial condition given. I just don't want to go through that process, but for you, you can just make up some initial conditions such as y of 0 equals 1 or 2, doesn't matter. Y prime of 0 equals some number to practice, but we are not going to go through it here. So let's just find the general solution. What we do is that we, again, by looking at it, we have, this is a linear. Obviously, it's a second order because of y prime, y double prime, and also constant coefficient, homogeneous. So linear, constant coefficient, homogeneous. That's really good. That means we can use the solution ansatz. Y equals e to the lambda x. Plug into the differential equation. We need to know the derivative. I'm just going to write down them quickly because at this point, I'm sure you all feel confident to find them. And then plug into the differential equation. We got lambda squared e to the lambda x minus lambda e to the lambda x plus 1/4 y equals 0. Y is e to the lambda x. Factor out e to the lambda x. We end up with lambda squared minus lambda plus 1/4 equals 0. Then we can write down the characteristic equation, lambda squared minus lambda plus 1/4 equals 0. And then we can solve for lambda here. You can try to factor this. You probably notice, you probably figure out the factors already. If you don't, you can use quadratic formula. Lambda 1, 2 equals negative b, negative 1 plus minus square root of b squared, negative 1 squared, minus 4 times a times c is 1/4 divided by 2a. And if you kind of take a close look at the square root part, we get 1 minus 4 times 1/4, which is also 1. So 1 minus 1 equals 0. So we just end up with positive 1/2. That's it, only one root, which means it's a repeated root. So that's important to know because it determines what the linearly independent root solutions are for the differential equation. So the base solution is going to be the first one, y equals, what do we have? We have lambda equals 1/2. So e to the 1/2 x. The second one will be similar to this, except that we have a coefficient x. So y equals x e to the 1/2 x. You can just use it directly on the exam. You don't have to show any extra work how to get the second base solution. Then the general solution is going to be C1 e to the 1/2 x plus C2 e to the C2x e to the 1/2 x. If we are required to find the specific solution, we can use the initial condition to find C1 and C2. But for the sake of time, I'm just going to leave it the way it is. Hopefully that's okay. Questions on this problem? I'm going to go over the next example, which is about higher order. Oh yeah. So you initially multiply the equation by 4 and solve without the fraction. Absolutely. That's a good point. So at this point, when we had the 1/4, or even the beginning, like when we had this differential equation here, we could multiply the differential equation by 4 on both sides. We still have a 0 on the right-hand side, right? So that's perfectly fine. So either places that you can multiply by 4 and solve. It might be easier to factor after we get the characteristic equation. Good point. Any other questions? All right, so the next example is y, the fourth derivative of y, so y to the fourth derivative, minus 5y triple prime plus 6y double prime equals 0. It's a higher order, it's not a second order, it's a fourth order. It's still linear, constant coefficient, homogeneous. So we can use the same solution ansatz. Y equals e to the lambda x, and we need the second derivative, third, and the fourth derivative. So when we find them, again, I'm going to do it quickly here. Probably not quick enough. Every time we take a derivative, we just end up with the extra lambda. And to put in into the differential equation, we have lambda to the fourth power e to the lambda x minus 5 lambda cubed e to the lambda x plus 6 lambda squared e to the lambda x equals 0. And then we can factor out e to the lambda x like what we did before. We have lambda to the fourth minus 5 lambda cubed plus 6 lambda squared. And we will require that this parentheses part equals 0 because the exponential part e to the lambda x cannot equal 0. So lambda to the fourth minus 5 lambda cubed plus 6 lambda squared equals 0. That's what we need. This is the characteristic equation. Even though we have a fourth power of lambda, we can try to factor this and then try to solve for lambda. So if we factor this, we take out lambda squared, we get lambda squared minus 5 lambda plus 6 equals 0. We can factor this further. So we have lambda squared. This one, if you factor it, you end up with lambda minus 3 times lambda minus 2, I believe, equals 0. That's good. So it means we can solve this, solve for lambda. From lambda squared equals 0, we get lambda equals 0. But be careful, because it's a lambda squared equals 0, we should have two lambdas. but we only have one value, so that means this value repeats. From lambda minus 3, we got lambda equals 3, and then we have lambda equals 2. Okay, so how do we write down the solution? Well, the base solution is going to be from lambda equals 0, we can use it directly. So that would be y equals e to the 0 x, which is just going to be e to the 0, right, which is 1. But let me leave it that way for now. And since lambda equals 0, it's a repeated roots. So we can write down the second one based on the lambda equals 0. So that would be y equals x e to the 0x, just like we did with the previous example. So that will give us 2 base solutions. And then the next one will be lambda equals 3. So that will be y equals e to the lambda, which is 3x. And then the last one will be y equals e to the 2x. Those are the 4 base solutions that are linearly independent. And you can simplify this one, really just become 1, this one become x. The other 2 stay the way it is. Then the general solution is going to be C1 times 1 plus C2 times x plus C3 times e to the 3x plus C4 times e to the 2x. That will be my general solution to the differential equation. If we have a higher order, we're just going to end up with more base solutions that we could solve for from the characteristic equation. But the idea, the approach is really the same as what we did with the second order differential equation. Any questions?
For all these questions, we're at the end of the question, we're going to be asked to find the solution interval. Is that correct or no?
If you want to find the solution interval, it's actually a lot easier. Personally, I think it's a lot easier to find them because we always end up with like an e raised to some, well, not always, right? But sometimes it's e raised to lambda x. The solution interval will be just negative infinity to positive infinity. We might end up with cosine and sine in there, like we did with, I don't remember maybe the first example. That's still going to be from negative infinity to infinity because it's sine and the cosine. It's actually coming from e to the ix, right, which is also all real numbers. So it's actually relatively easy if we do need to find a solution in it.
All right, thank you.
Yep, good question. Because it's really just it's a combination of a few exponential functions together, right? Exponential functions are always continuous everywhere. Doesn't matter how many of them adding together or subtracting from each other, pretty much always going to be all real numbers. But it's always good to be a little bit more cautious when you see it. I have one more example here, if you don't have more questions, which is we're going to solve this one. 2x squared y double prime plus 3xy prime minus 15y equals 0. So we're only going to look at x is positive with initial condition, y of 1 equals 0, y prime of 1 equals 1. If we look at the differential equation, it's still homogeneous because we get 0 on the right-hand side. And all the y terms are on the left. And it's still linear because we have y double prime, y prime, and a y. They all have power 1. There's no products of them. So it's still linear. And it's still second order. Right? But the difference between this example and the examples before this is that in this example, the coefficients, the 2x squared, the 3x, the negative 15, those coefficients are not constant. So non-constant coefficient. So if you will try to solve this using the same answer that we used before, I don't think it will work. Although I didn't try it. But how do we solve this? This particular example is what we call the Euler-Cauchy equations that describe the type of equations looks like some constant a x squared y double prime plus b x y prime plus c is a constant c y equals 0. It's easy to remember this type of equations by just thinking about when you have a second derivative of y, you get second power of x in front of it as a coefficient and then maybe some number a. When you have the first derivative of y, you get x to the first power in front of it as a coefficient times a constant. But when you have y, just y, there's no derivative, the zeroth derivative. When you have zeroth derivative, you're going to have x to the 0th power, which is 1. So basically it's a c times 1 times y. So that's the format of this type of equations. That's exactly what we have, right? We have 2x squared, y double prime x squared, and the y double prime go together. X goes with y prime, and the y goes with no x, just a number. So the given example is Euler-Cauchy. To solve it, we're going to use ansatz y equals x raised to the lambda. I believe Professor Gibson went through something like this in lectures. So that's the ansatz we're going to use. And to solve it, we just follow the same process we did before. We're finding the y prime, which is just using the power rule, bring lambda in front, and then subtract 1 from the exponent. So lambda x, lambda minus 1. That's the first derivative. The second derivative will be lambda times, again, use power rule. So that's a lambda minus 1, x to the lambda minus 2. Now we're going to take this, put into the equation. So we get 2x squared times y double prime. So that's a lambda minus 1, x to the lambda minus 2. Lambda minus 1, x to the lambda minus 2. Plus 3x times, we have lambda times x to the lambda minus 1. And then minus 15 y, which is x to the lambda equals 0. The process, to me, it's almost identical to the homogeneous constant coefficient in the linear equations. It's just the solution ansatz is different. And then what do is that we simplify by multiply all the terms together. For example, x squared times x to the lambda plus 2. When you multiply them, you add the exponents together, right? So that will give us x to the lambda. Same thing, this x times x to the lambda minus 1. Also give us x to the lambda. So what do we have? We have 2 lambda minus 1 x to the lambda plus 3 lambda x to the lambda minus 15x to the lambda equals 0. And then we can factor out x to the lambda from all terms. So that's a 2 lambda, lambda minus 1, you can multiply out, plus 3 lambda minus 15 equals 0. And if you remember that from when I wrote down the problem, we want to solve that differential equation for x greater than 0, right? So that equation is only for x greater than 0, which tells us that if x is positive, any positive number raised to the lambda is not going to equal to 0. The bracket part must be 0, so we get 2 lambda, lambda minus 1 plus 3 lambda minus 15 equals 0. This is what we call characteristic equation. Because the solution, the roots from this equation is going to tell us what the solution looks like, just like the previous example. And then this is going to, if we solve this, just expand it. So we get 2 lambda squared minus 2 lambda plus 3 lambda minus 15 equals 0. So that's a 2 lambda squared minus plus lambda minus 15 equals 0. And then we can solve it by factoring or by quadratic formula. I'll let you try either way, but I'm going to be a little bit lazy. So it looks like we can factor this as 2 lambda minus 5, lambda plus 3 equals 0. And if you use quadratic formula, you should end up with same lambda equals 5/2. That's the first one. Lambda 2 equals negative 3. And now we have those 2 lambda values. We remember we had the solution answer is y equals x to the power of lambda, right? So now we can write down the base solution. The linear independent solutions, that's going to be, the first one is going to be x to the 5/2 power. The next one is going to be x to the negative 3rd. And then we can write down the general solution, which is just like before, it's going to be linear combination of those two. So y equals c1 x to the 5/2 plus c2 x to the negative 3. I think this type of equation, it's good to practice now, even if it's not going to be on the exam, but it's the process, right? It's the same. You just have to remember that the answer is different. And then the rest is about finding C1 and C2. We just have to use the initial conditions, but we need to find the derivative first. And the derivative is really just power rule. So that would be C1 times 5/2 x to the 3/2 plus C2 negative 3 x to the negative 4. Remember, we take the derivative, we move the exponent to the front, and we subtract 1. Apply the initial condition. Y of 1 equals 0. So if we put 1 there into this general solution, so we get 0 equals C1. Well, 1 to the 5/2 is 1, 1 to the negative, so it's still 1 plus C2. And then we're going to use the second condition, y prime of 1 equals 1. I'm going to put this into the derivative we found. So we get 1 equals C1 times 5/2. Well, let me box this. That's from the previous condition. Now it's a new one. 5/2 times 1 to the 3/2 is still 1 plus C2 times negative 3. So this is the second equation. And if we solve this, we should be able to end up with C1, C2. I'm being a little bit lazy. I don't think I have the answer for C1, C2 here. Let's see. Okay, sorry, I'm just being lazy here. So that's 2/11. And then we just write down the solution. Y equals 2/11 x to the 5/2 minus 2/11 x to the -3. Those two terms, it's sort of equivalent to what we had, e to the lambda 1x and the e to the lambda 2x. In the second order constant coefficient example. But I just want to kind of show you the work side by side is really the same process, just the ansatz is different. And this ansatz works with this Euler-Cauchy equation. If you have something slightly different, maybe it's still second order, still linear, still non-constant coefficient, still homogeneous, it does not mean that this ansatz is going to work. Because it's only this ansatz is specific to this form. You have x squared, y double prime, x, y prime, and then no x, just y. That's what it was. All right, any other questions? Good luck on the exam. If you have any questions, feel free to send me an email, but I'm not sure if I'm going to be able to respond in time before your exam. But definitely reach out to Professor Gibson if you have any urgent questions about the exam. All right, take care, everyone, and I'll see you Tuesday. We'll be in person.